Now that we've gotten good at working with the multiplication axiom to help us count, we're ready to continue counting some problems that are a little more involved, but all based on that multiplication axiom. So what we're doing today is we're solving counting problems with permutations and combinations. And we're going to look at each of these separately and define them clearly. First, starting with the permutations. What a permutation is an ordered, emphasis on order because the order matters in a permutation, an ordered arrangement of elements. So, for example, we could ask maybe how many three-letter words can be made from the word math by rearranging these letters. And not real words. You've got M-A-T, M-A-H, M-T-H. You know, how many different combinations can we come up with? Well, the first character, second character, and third character need to be filled with one of these four letters. The first character can be any of the four letters. But once that letter is set in the first location, there's only three letters left to go in the second location. And once that's set, there's only two letters to go in the third location. And the multiplication axiom tells us that's 4 times 3 times 2, which is 24 different words. And we could try and list them all out. You know, there's M-A-T, there's M-T-A, there's T-A-M, there's there's 24 of them. We could even do this with a larger word. Maybe we could ask how many permutations can be made of the word. Let's see, we did finances in chapter 9, so let's say investor. Investor. Well, we've got how many letters? We're going to use all the letters, it looks like, this time. Actually, let's make this a little more interesting. Let's say it has to have a vowel in the first character. And let's do a second character also. Let's just keep it simple. First character and second character. So investor has 1, 2, 3, 4, 5, 6, 7, 8 letters in it. 1, 2, 3, 4, 5, 6, 7, 8 letters in it. The first character has to be a vowel. The second character has a vowel. The other ones can be whatever they want. So how many vowels do we have to choose from? Well, I's a vowel, E's a vowel, and O's a vowel. So there are 3 vowels to choose for the first location. Now that one of them is used up, there are 2 values for the second location. After that, it can be any letter it wants. Now, originally, investor had 8 characters in it, but we've got 1 already used in the first spot, 1 in the second spot, so there's only 6 characters left that can go in for the third location. then 5 left, 4 left, 3 left, 2 left, 1 left. And so basically we fill this in following the rules given to us in the problem, and then we multiply 3 times 2 times 6 times 5 times 4 times 3 times 2 times 1, and we do that on our calculator. And when we multiply it all out, there are 4,320 different ways to rearrange the letter of investor, where the first two characters are vowels. Now, there is a special type of permutation that tends to come up more often than the rest, and that is a permutation of n objects taken r at a time. And you'll see this abbreviated as, I'll do this in blue so it stands out, NPR. And some number of items is counted permutations selecting R of them. So, for example, out of 7 books, how many ways can 3 be placed on a shelf? Now, doing this 2 different ways. First, doing it with the multiplication axiom. I'll do the multiplication axiom here in green. We've got 3 books on the shelf. There are 7 in the first place, 7 choices for the first book, 6 choices for the next book, and 5 choices for the next book. And so we have 7 times 6 times 5, which is 210. There are 210 ways we can place these 3 books on a shelf, selecting out of the group of 7. Now, the other choice we could have done is we could have done it with this special permutation formula. There are 7 things, and we're doing a permutation and choosing 3 of them to place on a shelf. Well, our calculator can actually do these permutations for us. And the way we do this is we type in the 7, the total number of things, and then we go back to that math menu right underneath the alpha key. And all the way to the right, you can either scroll left once or right 3 times. You'll see number 2 is NPR. That's the permutation formula. So 7 NPR, we're going to select 3 of them. And when we hit enter, you'll see that also gives us the 210 possibilities. Now, with only selecting 3, the multiplication axiom was probably quicker. But if we're selecting more, maybe we're selecting 12 out of 400 possibilities, that might get a little involved, and this permutation option on the calculator is much nicer. So, what is the calculator exactly doing as we type that into the calculator? Well, what the calculator is doing is it's using a formula where it says NPR is equal to n factorial divided by n minus r factorial, where we define factorial as a number times the number below it times the number below it all the way down times 2 times 1. Basically multiplying the number by everything below it. And this kind of makes sense from the book example that we saw before. When we did the multiplication axiom, we did 7 times 6 times 5. I want to notice if we had done 7 factorial, that would have been 7 times 6 times 5 times 4 times 3 times 2 times 1. But we stopped at 5. So essentially what happened is we got rid of or divided out the 4 times 3 times 2 times 1, which is 4 times everything below it. That's 4 factorial. And that denominator, if I can continue working backwards, comes from taking 7 minus the 3 things we're choosing factorial. So you can kind of see where that formula comes from, the multiplication axiom, and then dividing out the books that we aren't using in this case. Now, fortunately for this chapter and what we're doing in this course, we don't need to use the formula. What I really want you to do is know how to set up the permutation and use your calculator to figure out the solution. So let's do another one where we try it on our calculator. Let's say, how many ways could a president, a vice president, secretary, and treasurer be elected from a club with 12 members? Notice we're selecting some out of the group. If we're selecting some out of the group, that is the permutation formula. The entire group has 12 members, and we're selecting a president, vice president, secretary, and treasurer. We're selecting 4 of them. So we're doing a 12 permutation for 12 math over to probability. Option number 2 is for permutations 4. And we see there are 11,880 ways this could turn out. 11,880 ways. Let's do another one. Actually, let's do a slightly different type of problem. Back out to 4 here. We did a line problem earlier where we lined up maybe 5 people in a line, and we found out that was 5 factorial. 5 times 4 times 3 times 2 times 1. But let's say we have a picky group of people. Let's say there's a small family of 3 that wants to sit together, keep that kid under control or something. So let's say, how many ways can 7 people sit in a line if 3 must sit together? So kind of visually saying this, if we've got, 7 people, we'll call them Adam, Brian, Catherine, Derek, Eric, Fiona, and Gregory. That's 7 people. And 3 of them must sit together. So just for the sake of discussion, let's say this first 3, the ABC group, must sit together. Well, what we can do is we can treat this ABC group as one entity or one person. In other words, there is one entity, that's the group, and then there's the D, E, F, and G. There are 5 sittings, if you will. So that means that group is going to sit down as 5 times 4 times 3 times 2 times 1. Notice everybody's sitting down. 5 times everything below it is 5 factorial. But then this one entity, this group, doesn't have to sit in that order. That group can move around within themselves. And so to account for that, we've got 3 for the first seat, 2 for the next seat, 1 for the next seat. Notice that's 3 factorial, 3 times everything below it. So to sit these 7 people in a line, 3 have to sit together. We've got 5 factorial times 3 factorial. We can do that on our calculator as well. We hit 5, and again we go to math and over to probability, and you notice option 4 is the factorial command. So 5 factorial, 3 factorial also, down to option 4. 5 factorial times 3 factorial is 720. There are 720 ways that these 7 people can sit in a line if 3 of them must sit together. How about this permutation problem? Let's say you have 3 magazines and 6 comic books. And we want to know how many ways can 2 magazines be on the left and 4 comic books be on the right on a shelf. Well, again, we're selecting a few out of the group. This is that permutation formula. However, we've got 2 groups we're talking about. We're talking about the magazine group, and we're talking about the comic book group. We're going to have to do those 2 groups separately. So first, for the magazines, there are 3 magazines, and we're going to select 2 of them. Similarly, for the comic books, we can do some type of ordering of them. There are 6 comic books, and we're going to select 4 of the comic books. The multiplication axiom tells us we just have to multiply these together to get the total number of possibilities. So for this, we can go to our calculator. 3, math, over to probability and down to permutation. 2, 3 permutation 2 times 6 math over to probability down to permutation. 6 permutation 4, enter. There are 2,160 different ways that we can arrange 2 magazines on the left and 4 comic books on the right on this shelf. How about this example? How many ways could, let's say, 8 people sit at a round table? I want to think about this for a little bit. Here's a round table with 1, 2, 3, 4, 5, 6, 7, 8 seats at it. And here's another round table with 1, 2, 3, 4, 5, 6, 7, 8 seats at it. And I want to consider, is this really a different arrangement? If we stick person A, Adam, on the right, and then we did B, C, D, E, F, G, H around the table, or if we stuck person A on the left, and then around B, C, D, E, F, G, H. Are these really different arrangements of the table? these really are the same exact arrangement because D is always by C and E. D has E to his left, C to his right. On the other arrangement, D has E to his left, C to his right. And we would notice that with any combination, any ordering on this table, that it doesn't matter how you rotate the table, you get the same arrangement. What this means is the first person to sit down doesn't really matter. The first person to sit down only determines the orientation of the table. What matters is the second person to sit down, because now you've got some type of ordering happen. That's when the ordering begins. So, of the 8 people, the first person to sit down, there are 7 to choose from. And then after that, there's 6, and 5, and 4, and 3, and 2, and 1. You notice we're multiplying 7 times everything below it. 7 factorial, 7 math. Go over to probability. Option number 4 is the factorial. 7 factorial is 5,040. There are 5,040 different ways to sit at a round table for 8 people. Let's do a variation on this. How many ways could 4 men and 4 women sit at a table with alternating gender? Maybe it's a large blind date. We got 4 guys and 4 girls. They're going to sit every other, and they're going to find out who their date is when they sit down. Whatever the case might be. So we're going to do this with factorials, but I want to set it up by looking at the arrangement. There are 8 seats at the table, and it's a round table. Again, since it's a round table, the first person to sit down doesn't matter. That's just setting up the arrangement or the orientation. There's no ordering with the first person to sit down. The second person to sit down, though, has to be the opposite gender. So how many of the opposite gender are there? Well, there's 4 of the opposite gender. Actually, let's do different colors for the different genders. Let's do the opposite gender in orange. So 4 for the opposite gender. And then we have to go back to the green gender. I didn't really specify men or women. It doesn't really matter. The first person to sit down determines the orientation, and then we alternate. We've already got 1 green person sitting down, so there are 3 green people left. Now we go back to orange gender, and we have 4 of them total. 1's already sitting down, so there are 3 left to choose from. And then you start to see the pattern arrangement begin. There are 2 of the other gender remaining, and then alternating gender there are 2 remaining, and then alternating gender there are 1 remaining, and then alternating gender there's 1 remaining. And so you see the green gender, the gender to sit down first, the first person didn't matter, but we took 3 times everything below it. The orange gender, whatever one that was, we took 4 times everything below it. So it's kind of similar. We've got an orientation of 4 and an orientation of 4, but the first person overall doesn't matter. So we end up with 3 factorial times 4 factorial, which we'll do on our calculator. 3 math over to probability. Option 4 is the factorial. Times 4 math probability. Option 4 is the factorial. There are 144 different ways we could set up this alternating gender. Here's another classic problem of permutations where the order matters. We have an ordered group of elements. We want to know how many permutations can we make of the word Mississippi? And this is really a classic problem because Mississippi is different than the example we started with. Example 2, we did the word investor. What's different about the permutation of investor and the permutation of Mississippi is Mississippi has a lot of repeating letters. So if we were to switch the order maybe of this S and that S and this I and that I and the P's, the word hasn't changed at all. It's still the same word. So it doesn't count as a new permutation because we've got a repeat happening. So what we have to do is get rid of the repeats. And the way we get rid of the repeats is we are going to, similar to the permutation formula, divide out the repeats. So if this was a normal word with all unique letters, Mississippi has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. 11 factorial would tell us how many ways we could arrange those. But we have to divide out all of the arrangements of repeated letters. Notice we've got the I as a repeated letter. I is there 1, 2, 3 times. So we're going to divide out all the ways those 3 letters can be rearranged, which is 3 factorial. We also have the letter S repeated 1, 2, 3, 4 times. Dividing out the ways those could be arranged is 4 factorial. Whoops, I missed an I, didn't I? There's actually 4 I's. Need to fix that. 4 I's, so not 3 factorial for the first one. This is why it's good to color code, so you see if you missed one. There are 4 I's, so we will divide out 4 factorial. There are 4 S's, so we will divide out the 4 S's. And finally, there are 2 P's that are repeated, so we have to divide out the 2 P's. 2 factorial. Only 1 M, so the M is okay. So what we're really doing is taking 11 factorial divided by 4 factorial, 4 factorial, 2 factorial. As we type this into our calculator, we need to make sure the calculator knows all that stuff is in the denominator. Otherwise, it'll think the last 4 and the 2 are in the numerator, and that's wrong. So make sure the denominator is in parentheses because there's a lot of stuff happening there. So we have 11 math over to probability, 4 is factorial, divided by, in parentheses, 4 math, 4 is factorial, times 4 math factorial, times 2 math factorial, close the parentheses. Whoops. So 11 factorial divided by 4, 4, and 2 factorial. How many ways can Mississippi be rearranged? 34,650. 34,650 ways we can rearrange the letters of Mississippi to get different unique words. Most of them nonsensical words, but there's 34,000 different unique words. This is similar, that was number 8, this is similar to if I wanted to toss a coin 5 times. This is where we start setting up the probability that we're going to see tomorrow. A coin is tossed five times. How many have 3 heads and 2 tails? Couple ways we could do this. But let's try and do it with this Mississippi style problem. It's tossed 5 times, so there are 5 factorial different options. The problem is we want to get rid of the repeats. For example, we want 3 heads, 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 and 2 tails, tails, tails. And we're going to say the order matters here. We want to do all the different arrangements, but we've got a repeat of 3 heads, so we've got to divide out the 3 factorial, and a repeat of 2 tails. Divide out the 2 factorial, just like the Mississippi problem. 5 factorial, divided by, make sure that denominator is in parentheses, 3 factorial times 2 factorial. There are 10 different ways that when we toss a coin 5 times, we get 3 heads and 2 tails. And from there, you can see the easy transition to start talking about what's the probability that a coin is tossed 5 times and you get 3 heads and 2 tails. But that's going to have to wait for another day. So those are permutations. The order matters. What we're going to take a look at next are what are called combinations. Combinations are arrangements where the order does not matter. I'm selecting 2 out of the 5 options, and I don't care which one I get first and which one I get second. And the way we show a combination is similar to the permutation. You've got a number of things, and we're going to select R of them. We just use the letter C instead of P to represent combination. And it's very similar to the permutation formula, where we take n factorial divided by n minus r factorial. But then we have to account for the fact that order doesn't matter. And very similar to the Mississippi problem, we just have to divide out those repeats. And those repeats are all of the things we selected factorial. So that's the only difference in the formula. That divides out and eliminates the repeats. But again, I don't care so much about the formula here as long as you can use it. So if there are 7 things and we're going to choose 3 of them, we can do that on our calculator. Very similar to permutations, we type in 7, math, over to probability, and you notice option number 3 was in CR. We're going to select in CR to get 7, choose 3 items, and hit enter, and we find there are 35 ways to select 3 out of 7 things where we don't care about the order. How that looks in a problem is you'll see a question like how many ways can a group of maybe 8 people select 2 members to represent them in contract negotiations. Now here it doesn't matter which member gets selected first, which member gets selected second. We don't care about the order. We just care that out of the group of 8, we're going to choose 2 of them. And again, we'll just do that on the calculator. 8, math, over to probability. Option number 3, NCR. We're going to choose 2 of them. There are 28 ways this group can proceed. A classic example of these combinations is, let's say there are 15 people at a party. And of course, in the good spirit of friendship, everybody has to greet everybody. So everybody's going to shake everybody's hand. We want to know how many handshakes are needed if everyone greets everyone. Well, again, we don't care the order of the handshake. I don't care if Sue meets Maria first or if Maria meets Sue first. The order doesn't matter. So this is a combination. There are 15 people, and we want all the ways we can select out of the group of 15, 2 of them to shake hands. And that'll give us all the different combinations of 2 handshakes in the group of 15. Calculator doing the hard work for us. 15 math over to combination 3. Oops, 2. So we're going to do 15, choosing 2 of them. There are 105. Was that right? Yeah, 105 handshakes at this party of 15 people. Let's do another problem that's a variation on this thing. Let's say that the streets of a neighborhood are 6 blocks long and 6 blocks high. It's a grid. And let's say we want to go from the bottom left to the top right. We want to know how many ways can a person drive from the bottom left to the top right. So kind of drawing a picture of what's happening. We're 6 blocks long, so that's 1, 2, 3, 4, 5, 6, and we're 6 blocks high. 1, 2, 3, 4, 5, 6. So kind of drawing the grid in here. Not really to scale, but we'll go with it. So it's 6 blocks across, 6 blocks up. Essentially what we want to do is go from the bottom left to the top right, and we can get there however we want to. Maybe we'll go over a bit, we'll go up a bit, we'll go over up, go over quite a bit, and then finally up. But what I want to notice that we had to do to get there is we went, we'll just call it right, right, up, 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 and then we went right, up, right, 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 and then finally ended with an up, and we got to the end. What we have there is we went right 1, 2, 3, 4, 5, 6 times. We also went up 1, 2, 3, 4, 5, 6 times. And that kind of makes sense, because we had to travel a total of 6 right and a total of 6 up. And it doesn't really matter which order we did things in. What we have is we have a combination where we are going to make 12 directional movements. We have to move right 6 times and up 6 times. We have to do 12 of them. Let's see if I can keep the problem on here. But it doesn't matter which order we do them, so we're going to basically choose some of them to be right, and all the rest are going to have to be up. How many do we choose right? Well, 6 of them right, because we're going to move to the right 6 times, and all the rest of the movements are going to be up. So 12, choose 6. 12, math. It's a combination, number 3, because the order doesn't matter. We're going to do 6 of them. And when we hit enter, there are 924 different ways that we can go from that bottom left corner to the top right corner by just changing the pattern of rights and ups and ups and rights. Lots of ways to get there. Which way's quicker? Guess you have to try them all. How about this problem? This is a common problem that's addressed in committees in the Senate. Let's do it with smaller numbers, though. Let's look at the question, how many committees could be formed of 3 Republicans and 2 Democrats be chosen from 8 Republicans and 10 Democrats. So maybe there's only 8 Republicans eligible for this committee, 10 Democrats eligible for this committee, and we're going to choose 3 Republicans and 2 Democrats. How many ways can we do that? Well, we have to treat each group again separately because the groups aren't going to mix. If we end up with too many Republicans or too many Democrats, this committee doesn't work. So we're going to do a combination for the Republicans and a combination for the Democrats, because again, the order doesn't matter. There are a total of 8 Republicans to choose from, and we are going to choose 3 of them. There are also a total of 10 Democrats to choose from, and we are going to choose 2 of them. The multiplication axiom tells us that if we want the total, we just have to multiply these together. So we have 8, math, over to probability and down to combination. 8 choose 3 times 10, math, over to probability and down to combination. 10 choose 2. There are 2,520 different committees that could be formed out of this group with 3 Republicans and 2 Democrats. We can use this idea of using different combinations for each case and each situation for the classic probability question that everybody always asks about, poker. Let's look at this poker question. How many 5-card hands are a full house? Now, a full house means a 3 of a kind and a 2 of a different kind. Well, to do this, we're going to need combinations for each situation. First, let's look at the 3 of a kind. In a deck of cards, we need to first select the number that's going to be the 3 of a kind, maybe the queens. We're going to have a 3 of a kind of queens. So, combination, doesn't matter the order, how many numbers are there to choose from? In a deck of cards, there are 13 numbers. We are going to choose one of those numbers, the queens, in order to focus on. But we don't want all of the queens, we only want 3 of the queens. So we need another combination. There are 4 queens total in a deck, and we are going to choose 3 of them. So the number of ways we can get 3 of a kind out of 3 cards is 13 choose 1 times 4 choose 3. But now we want to get also a 2 of a kind. We'll do it in a very similar way. We need a combination to choose the number. But this is important, is the 2 of a kind has to be a different number than we chose before. So now there are only 12 suits to choose from. 12 numbers to choose from. Maybe we're going to do aces this time. we're going to select one of those 12 numbers, the aces, in order to focus on, and we need a combination to tell us how many of those aces we're actually selecting. There are 4 aces to choose from, and we're going to select 2 of them to make our 2 of a kind. Multiplication axiom says if we multiply it all together, we will find the total number of full houses possible in a poker game. There are 13, math, probability. We're going to choose 1 times 4, math, over to probability. Number 3, we're going to choose 3 times the green ones, the 2 of a kind, 12. Missed the 1. 12, there we go. Math, over to probability, down to combination. 12, choose 1, times 4, math, choose 2, and when I hit enter, I find there are 3,744 different full house hands possible in a game of poker. Now we're chomping at the bit to get to probability to see what is the probability that I get a full house, but that is another lecture. Right now I want to do one more example. Let's say a club consists of 2 advisors, 8 sophomores, and 11 freshmen. We want to know how many ways can one select let's start with a group of 1 of each. We want to get 1 advisor, 1 sophomore, and 1 freshman. Well, again, we can't mix them, so we need a different combination for each group. So first, the advisor. There are 2 advisors to choose from. We're selecting 1. Of the 8 sophomores, there are 8 to choose from. We're selecting 1. And of the 11 freshmen, let's do them in a different color. Of the 11 freshmen, there are 11 to choose from. We're going to choose 1. 1 of each. 2 choose 1, times 8 choose 1, times 11 choose 1. And when we do that on our calculator, I think we get, well, let's just do it. 2 math choose 1 times 8 math over to probability. Option number 3 is choose 1 times 11 math over to probability. Choose 1. Enter. There are 176 different ways we could choose 1 advisor, 1 sophomore, and 1 freshman. Let's do a variation on a theme here. Let's say we do a group of 3 with no freshmen. Maybe it's the freshman initiation group, so no freshmen allowed. Well, we know we're going to do a combination because the order doesn't matter, but how many do we have to choose from? We can choose from either the 2 advisors or the 8 sophomores. There's a total of 10 to choose from, and we're going to select 3 of them. So, doesn't matter how they overlap or how it works. So we've got 10 math over to probability. NCR, we're going to do 10 choose 3. There are 120 different groups that have 3 people in it with no freshmen. Let's do one last variation on a theme. We're going to do a group of 3 with at least 1 advisor. Probably should have a question mark. Now here we've got 2 choices. We can either do a group of 3 with 1 advisor or a group of 3 with 2 advisors. Technically 3 advisors also, but there's no way we're going to end up with 3 advisors. There's only 2 to choose from. So what we're going to do is first look at the option where there's 1 advisor. So of the 2 advisors, we're going to choose one of them. Then of everyone else, how many other people are there? Well, there's 8 sophomores and 11 freshmen. So there are 19 other people to choose from. And we've already got 1 person that's an advisor, so there's 2 more spots available to be selected. The other option is, instead of choosing 1 advisor, of the 2 advisors, we choose both of them. Now we've got at least 1. Technically, we have 2. Now for the everyone else, there are still 19 everyone else's to choose from, but this time we only need 1 other person to get our committee up to 3 people. Now we know we multiply the combinations together to get the total numbers, but these 2 groups are exclusive. We're saying we don't want both of these to occur. We want one or the other to occur. And in the situation where we've got an or, one group or the other to occur, we're going to add those groups together. So what we want to actually calculate here is 2 math over to choose 1, 2 combination 1, times 19 math down to combination, choose 2, plus the other option, which was 2 math combination 2 times 19 math combination 1. And the total number of ways we can choose this group of 3 is 361. There are 361 ways we can get a group of 3 that has at least 1 advisor. So that's what we're looking at today, are permutations and combinations. There are lots of different variations of these problems. I can't show you all of them, but what I want you to do is think through them. Figure out, is this a permutation? Is this a combination? Is this a factorial? How do I divide out the repeats? Does the order matter? Are they in a line? Are they in a circle? How does that matter? I want you to work through this a little bit. I will quickly review the formulas that we saw today, all in one place here at the end of the video. Let's say we've got an arrangement of n unique items. We've got 5 people, they're all getting in a line. That was n factorial. N times n minus 1 times n minus 2, 3, 4, all the way down to 2 times 1. N times everything below it, because we used all of them. Now, if we didn't use all of them, and we just want an ordered list, an ordered arrangement of R out of n items. So we're not using all of them, we're using just maybe 5 out of 7. That is the NPR, because the order matters, it's a permutation. And that formula was n factorial over n minus r factorial. And then we said if the order matters, order does not matter, sorry. If the order is not important, and we choose R out of n items, that's the combination formula in CR, which is very similar. N factorial over n minus R factorial. We just divide out the repeats of R factorial. And that was connected to the idea of omitting repeats. We divide them out. This was what is classically called the Mississippi problem. And that was n factorial, and then we divided out all the repeat factorials, the k1 factorial, k2 factorial, all the way down to the last one that's repeating factorial. We can omit the repeats. The only variation on the theme that we saw, it's not really a formula, but I'm going to put it on here anyways, the circle arrangement. And there were a couple variations on a theme of the circle arrangement. But in general, with a circle, the first person doesn't matter, so we start with one less than that, factorial, to find out how many ways that circle can be arranged. So a lot of helpful formulas to work with the multiplication principle to help you count things with permutations and combinations. There's a lot of different variety of variations of these problems. Take a look at them, see what you can work out. Come to class tomorrow with questions, and we will see you then.